As far as Bronsted goes, this is neither an acid or, it's not a proton donor, it's not a proton acceptor, right? Neither. But as far as Lewis goes, what do you think?
Acid.
It's an acid. Why? How did you come up with that?
No, there's nothing in orbital, it's electron poor.
It's electron poor, right?
Electron.
Yeah, basically, it's, it doesn't even have an octet. Can we double bond? Can we double bond fluorine? No, fluorine does not double bond. It doesn't want to lose that electron density. And so this is a powerful Lewis acid. And we can react it with Lewis base like ammonia. This Lewis base attacks here. Then we end up with this compound here, which looks weird. But we end up getting. So this would be another example of a Lewis acid-base reaction. And we'll talk more about analyzing Lewis acid-base reactions later. And so for this next test, you don't need to know much about Lewis acid-base reactions. This is called a mechanism where you draw arrows showing how the electrons move about for this. All right, other questions? The other question was about oxidizing acids versus mineral acids. And I know Sherry looked up on Wikipedia what a mineral acid is. For example, they said nitric acid is a mineral acid, but I would disagree with that. I would consider nitric acid as a oxidizing acid. And so one of the things you could do is to take a look at all the acids on the redox chart and see if you can see a pattern there. Okay. All right, other questions? So try that and see what you come up with, and maybe you'll see it. All right, we're going to continue with chapter 6 today. And we're talking about pressure. Pressure there are two kinds of units for pressure. There's your regular unit, and then there's a depth unit, like how deep you are. So, for example, if we're at sea level, how deep in the atmosphere are we? How high does this atmosphere climb up? I mean, well, how thick is the atmosphere? I was supposed to look that up. 30 miles?
No, 20.
20 miles? Okay. And so, basically we could say we're 20 miles deep in the atmosphere. And so rather than saying 1 atmosphere, we could say, oh, it's 20 miles. Something like that. Does that make sense? That's how deep we are. Or rather than being 20 miles under the atmosphere, we could say, well, that 20 miles of atmosphere weighs how much in terms of water or in terms of mercury? In terms of mercury, it's quite easy because mercury is so many more times dense than air that this would be about 760, actually I should say 1 atmosphere is 760 millimeters of mercury, liquid mercury. And so you could be submerged under 20 miles of air, or you could be submerged under 760 millimeters of mercury. They would exert the same pressure, the same weight on you, right? And then in terms of, mercury is not the only liquid around. We could figure out how much water. What was the density of mercury relative to water? 13.59. And so we need 13.59 times, times the amount of mercury we have. And so we'll just say for every 1 millimeter of mercury, we need 13.59 millimeters of water, or whatever units we want, millimeters, feet, yards, miles. So if we had 1 mile of mercury, we'd need 13.59 miles of water to be under. And so this comes out to what?
3 times 3.
What was that, 1.0? 10 to the 4? So about 10,328.4 millimeters of liquid water. So this would be equivalent to 10,328 millimeters of H2O liquid. And so in other words, 20 miles of atmosphere would weigh the same amount as 760 millimeters of mercury, which would weigh the same amount as 10,328 millimeters of water. And so now we can look at doing a problem. And the problem is going to be this. Did we finish that one with the pool, the world's deepest swimming pool? So let's figure out the pressure. We're going to make an assumption. We're going to say that the air pressure that day weighs, or is 1 atmosphere. This is the air. Okay, so we have 1 atmosphere of air weighing down here, and then we have this pool that goes down 131 feet of H2O liquid. And so at the bottom of this pool, what is the total pressure?
A lot.
A lot. And so this is what we can do. We can figure this out. Let's just get it in terms of liquid mercury, both pressures, the air pressure and the water pressure in terms of liquid mercury pressure. And so the air pressure, this in terms of liquid mercury would be 760 millimeters of mercury. And so this would be like, rather than having this 20 miles of air above us, we could think of this as being a pool of mercury, 760 millimeters deep, about 3/4 of a meter deep. And then the water, what we're going to do is we're going to convert that into millimeters of mercury. That is, what would the equivalent amount of mercury be for 131 feet of water? And so we know that for every 1 foot of mercury liquid, we would need 13.59 feet of water liquid. And then we'll convert from feet to inches. That is, 1 foot is equivalent to 12 inches. And then inches to centimeters, 2.54 centimeters per inch. And then centimeters to millimeters, 10 millimeters per centimeter. And this gives us how many millimeters of mercury that water?
39,920.
39,000.
39,929, actually.
39,929 millimeters of mercury. We aren't being too exact here. Which is going to give us a total of
No.
39 meters. This would be about 39 meters, which is, I think you just converted the feet into millimeters.
Yeah, that's fine.
But did you do this one? 13.95?
Well, that is ahead of me.
All right.
It's 22.43.
22, what is it? 43? 22.43? Okay. Millimeters.
That's right there.
Well, 2.54. Not by 13.
I thought there's 760. I thought there's 760 million.
All right, let me try this again.
2,938.
Yeah.
2,938?
That's mercury, sorry.
2,938 millimeters of mercury. And so being under 131 feet of water would be like being under 2,938 millimeters of liquid mercury. And so we can add these up now. So we have 760 plus 2,938 gives us how many total?
3,698.
3,698 millimeters of mercury. And then how many atmospheres is that? Convert that to 4.86 atmosphere? 4.87? We'll just say 4.9. 4.86 or 7. 4.9 atmospheres. About 5 atmospheres. So at the bottom of this pool, the pressure of 5 atmospheres. It'd be like having 5 of these on top of you. 5. No, I don't think I could handle that. Actually, it's huge.
I have a question.
Uh-huh.
Where did the feet of mercury, how did you find that relationship with the feet of water?
Oh, how did I find it? Because 1 gram of water is per milliliter is the density. 1 milliliter of mercury is 13.59 grams. And so mercury weighs 13.59 times the weight of water. And so this is just to see the by conversion. We could do, in your book, they go through a more proper dimensional analysis procedure for this.
Chapter 1 book.
Yeah, and so I just did this. But we'll talk more about gas pressures later. But this is just to get you thinking about liquid mercury and how it relates to pressure, because technically pressure shouldn't be height or length, meters or feet or whatever. Pressure should be force per unit area. And so when we're thinking about 1 atmosphere of pressure, the normal atmospheric pressure, we think of 14.7 psi, is that right? For 3 sig figs? 14.7 psi, what is that? That's like pounds of weight per square inch. So 14.7 pounds for every square inch. That's force per unit area. Or it's about equal to 1.03 ... times 10 to the 5th.
No, 1.013.
1.013, thanks, times 10 to the 5th pascals. You know what a pascal is? It's a SI unit of pressure, and it's newtons per meter squared, where newtons is the weight of the force. And so these are your typical pressure units: pascals, psi, even bar. This is 1.013 bar, which is the SI, the metric system. In other words, it's about, 1 atmosphere is about 1.0 bar. Not exactly, but close. And then we start getting into all these other things. 1 atmosphere is also equivalent to 760 millimeters of mercury height, which is equivalent to, what was that? 2,000, 760 times 13.59? Yeah, 10,000 millimeters of water, which to a liquid. Turns out 10,000 millimeters of water is like 3 stories high, so you'd be 3 stories deep, roughly. Yeah. Is that right? 10 meters? Yeah, about 30 feet. So you'd be about 30 feet deep in water. 30 feet. Etc. All right, then later on we'll talk about the barometer and the manometer. For today, I want to just go ahead and jump into chapter 6. I'd like to get a good chunk of chapter 6 out of the way. So in chapter 6, we have the ideal gas law. PV equals nRT. Any problems with this? No. The calculation is pretty straightforward, right? Most of them aren't so difficult. And so we have our standard PV equals nRT calculation, where you have the pressure, the volume, number of moles, and temperature. And then we have some applications of this. So for example, the density of a gas. The density of the gas is the mass divided by the volume. The volume we can calculate from PV equals nRT. V is equal to nRT over P. Do mass over nRT over P. This gives us mass over N times P over RT. Mass over N has the units typically of grams per mole. And so grams per mole is just what? The molar mass. So we'll just have this, and I'll use this symbol, double M here for molar mass. The molar mass times P over RT. All right, the nice thing about this equation is we don't have to do any experiments. In other words, we can calculate density of a given gas at any T and P. And so whatever temperature or pressure you're interested in, just do a simple calculation, as long as you know what the molar mass of the gas is. So let's do an example calculation here. Say, what is the density of air at 1? We'll do RT. Do you know what RT stands for? RT stands for room temperature. What is room temperature? Well, room temperature varies, but we have a fixed one.
20 degrees.
25 degrees C. That's our fixed room temperature. It's not 25 degrees C in here, I don't think. Okay, and 1 atmosphere. And 2, let's do this calculation. I think at the top of Everest, let's say we have a temperature of 5 degrees C and a pressure. Atmospheric pressure is going to be like higher or lower on top of Everest? A lot lower. I mean, you're much higher up. You don't have as big of a blanket. And also, the heavier molecules are going to sink to the bottom. The lighter ones will go up. And so 5 degrees C, and let's go with 0.3 atmospheres. So all we
In a room, in a room,
No, it doesn't have to be in a room, just wherever you're at. 5 degrees C. This one's room temperature, but it can be outside too. 25 degrees C. It doesn't matter. It doesn't have to be inside. All right, we run into the first problem. You might have run into this in Chem 4, you might not have, but is air a pure substance? No, air is a mixture, right? And so if I'm thinking about air, let's just say we're going to assume air is 80% nitrogen and 20% oxygen. It's close enough. It's more like 21%, but just keep the numbers clean and simple. And so 80% nitrogen, 20% oxygen. And also the composition is going to change. Like if you go to the top of Everest, it'll be enriched in the lighter component, which is nitrogen versus oxygen. And so the proportions are going to change a little bit. But we'll just assume it's fixed at this percentage. And so how do we tackle this? What should we do? Should we calculate the density of nitrogen and then the density of oxygen? Or what? And so we've dealt with mixtures before. When you've had mixtures, there are different ways you could deal with it. A couple of the ways you've dealt with it is using the graphing method or multiple equations. But let me show you a different way of tackling this problem. And the different way of tackling this problem, we're going to calculate the molar mass of air. And so, can we calculate the molar mass of air? And the answer is yes, we can calculate the molar mass of air. Just the same way where we calculate the average atomic weight or average atomic mass. Now, this seems to make sense. There's some kind of residue here. I wasn't here this morning. There's something hit here. And this candle wasn't taped on here this morning. So, I was wondering what that was. Anyway, for example, the average atomic mass of oxygen is the average of all the naturally occurring isotopes, right? And we have a weighted average for that. And the same thing, we use the exact same type of equation to determine the molar mass of air. The molar mass of air is going to be a weighted average depending on the proportions here. And so the molar mass of air, using the same equation that we did for isotopes, is 80 parts out of 100 nitrogen. And what's the molar mass of nitrogen? Well, it's 28.02 grams per mole. And then we'll add 20 parts out of 100 will be oxygen. Oxygen is 32.00 grams per mole. And so what we'll end up with is a weighted average, the average molar mass of air. And so this is going to give us what? Okay, 28.8, let's go with that, grams per mole. I'm not allowed that many sig figs because I'm just ballparking the percentages here. But does that make sense? This would be the average molar mass of air. Now that I have the molar mass of air, this mixture, am I going to find a molecule that has this mass? No, just like I'm not going to find an atom of oxygen that weighs 15.9994. That's just the average. Right? It's not what it actually weighs. Well, the same thing here. I'm going to find molecules that have this mass and molecules that have this mass, but none that have this mass. Well, I can still use this, and if I just go ahead and calculate the density of air under these conditions, this is for one, the density of air is equal to the molar mass of air, 28.8 grams per mole, times what? Molar mass times RT over P. Is that it? P over RT. Molar mass times P. Pressure is 1 atm, or 0.08206 liters times atmosphere divided by mole Kelvin. Yeah. And the temperature, 298 Kelvin. So let's make sure the units work out. So the Kelvin cancels, atmosphere cancels, moles cancel. And that gives me grams per liter. So that sounds right. The units are right. And so what is the density of air of RT in 1 atmosphere? 1.1? 1.18 grams per liter. All right, so that's the density of the air for conditions 1. What about for conditions 2, where we have the temperature of 5 degrees C and a pressure of 0.3 atmospheres? 28.8 grams per mole times 0.3 atmospheres over 0.08206 liters atmosphere mole Kelvin times 278. 1.26. 1.26. Something seems off. I'd expect air to be less dense on top of Mount Everest, rather than more dense.
0.379.
Yeah, I got
Okay, 0.37. 0.37, 0.38 grams per liter. So quite a bit less dense, as you'd expect. 38.
Just rounded, it should be a 9 then.
Okay, 0.381.
No, it should be just 0.
I mean, what comes after the 8? 7? 387? Okay, we'll go with that.
3787.
3787. 7, 8. Although everybody should be getting the same number. We aren't allowed that many sig figs, one sig fig, so about 0.4 grams per liter, about 1 gram per liter. So this is another way. For gases, we can calculate the average molar mass of a mixture. We don't necessarily have to do it graphical. If we did this graphical, how would he set it up? Now, if we did this graphically, we do 100%, 0%, and we do the heavier one, so 100% O2. 100% O2, then the density is just going to be pure O2. 0% O2, then the density is just going to be pure N2. And then we would have a graph like this where we'd look, at 20% O2, at 20% O2 we would have what density? Is that right? And so we could do this graphically for part 1 and then repeat graphically for part 2 if we wanted to, but it's not necessary in this particular problem, because we could calculate the average molar mass. Okay, so just another way of tackling a mixture problem, etc. Now, another thing that's determined from the ideal gas law is the molar mass of a gas. The molar mass of the gas can be determined experimentally if we know the mass of the gas divided by the moles of the gas. Moles of the gas, we can use the ideal gas law, which is just PV over RT. And so this is going to be the mass times RT over PV. So if we measure the mass of the gas, its temperature, pressure, and volume, we can determine the molar mass of the gas. And so for air, we can trap a sample, weigh it, determine what its pressure, temperature, and volume is, and then we can get the molar mass of the air sample. Or if we had a pure gas, we could do the same thing. Or if we knew the density, you see mass over volume here is just density. If we have the density, we can do an additional calculation of mass. This gives an alternative to measuring the weight of a gas. How do you measure the mass of a gas, the molar mass of a gas? Mass spectrometer. So you don't have to buy a fancy mass spectrometer if you take some measurements. The only problem with these measurements is there's a lot of uncertainty when you do those. The numbers aren't so precise. They're just difficult to measure. All right. The next part of this is the universal or the combined gas law, this chapter. So let's talk about that. A lot of people have done these types of problems. Not too much difficulty. PV over NT is just equal to R, which is a constant. And so what we can do is we can set one set of conditions, P1, V1 over N1, T1, equal to another set of conditions, P2, V2 over N2, T2. And just vary. Well, for example, vary the volume and see what happens to the pressure. Vary the temperature, see what happens to the volume. Those types of calculations. The only difference between this equation and the one you used in Chem 4 is that now we have the moles. In Chem 4 they kept the moles the same, that is, the gas was sealed. But in this case we can inject more moles of gas or we can suck moles of gas out of it to see what happens to the physical property of that gas. So this is the combined. We'll take a look at some of the homework for that. And then after the combined gas law, then we go on to stoichiometry, gas stoichiometry. We'll do some examples of some of these later. Let me just cover the major topics first. So in stoichiometry, we do a mole-to-mole conversion using a balanced chemical equation. For gases, we just have an alternate way of going to moles. So for example, if we start off with a volume of a gas, then we can go straight to moles. There are two ways to go to moles. One, we could just calculate it using the ideal gas law. N is equal to PV over RT. Just do a calculation. Or two, we could use something called molar volume, MV. Most people have 1 molar volume memorized. Do you have a molar volume memorized? The molar volume that most people have memorized is this. 22.4 liters per mole. 22.4 liters of gas per mole of gas. But it's restricted. Under what conditions is this true?
Standard temperature and pressure.
Yeah, standard temperature and pressure. So this would be at STP. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. At 0 degrees Celsius, is that very useful for us? No, not at all. Yeah. And so this is not the number you should memorize. The number you should memorize is the molar volume at RT and 1 atmosphere. If you're going to memorize one, this is the one you're going to use the most. What is RT? Room temperature. So go ahead and calculate the molar volume for me using this equation. The molar volume is equal to the volume per mole. And we could do a quick calculation here. The mole is equal to PV over RT. And simplifying, we just get RT over P. Or we could substitute for V. It doesn't matter, V or N. We get the same answer. And so go ahead and calculate the molar volume at RT and 1 atmosphere. Someone have it? 24.45? 24.45 liters per mole at RT in 1 ATM. That's right. And so this number is going to be a heck of a lot better to memorize because here, let's say we had 24.45 liters of A gas. How many moles is that? Well, that's 1 mole. You know, we'll just flip this over. 1 mole of gas for 24.45 liters. And so we could go direct into moles of A and then just continue on using conversion factors. This is a standard stoichiometry problem. And we can reverse this by, just going backwards using the. But in Chem 1A, you're going to have to deal with mixtures more. And so sometimes rather than given a pure gas, A, we have a mix. And we could have a mixture of, A, B, etc. For example, air. If we have a mixture like air, then air is not pure O2 or it's not pure N2, it's a mixture. And so how do we go from here? Well, we need to know the composition of the mixture. And there could be multiple steps here or a single step. And so let's take a look at that right now. So for example, when you're using air for combustion, we want to know how much O2 is in the air, correct? And so let's say an example is this. Air, 20% O2. Okay. What does that mean? Does this mean I have 20 liters of O2 for every 100 liters of air? No? Or does this mean I have 20 grams of O2 for every 100 grams of air? True or false? True or false? Or does this mean I have 20 atmospheres of O2 for every 100 atmospheres of air? So what is it? We used this percentage before in an earlier calculation, but you know what? I skipped over entirely if it was correct or not to use that. Or does it mean we have, sorry, let me continue up here, 20 moles of O2 for every 100 moles of air, which is the same thing as like 20 molecules of O2 for every 100 molecules, same ratio of air, the moles and molecules. What is it? How about this one? 20 moles of O2 per 100 moles of air, true or false? False? False. True or false? False? True? False? Okay. You got 100%. 100% bronze, unfortunately. This one is true. This is true. This is true. This is true. It doesn't seem like it should be true, though. There's something that seems wrong about this, and there is something that's wrong about it. This is something you just have to memorize because I didn't tell you yet, but gases, when we're given a percentage, the percentage is not a mass percent. gases typically are given as mole percent. And so this mole percent or molecule percent is always true. But what's tricky are these volume percent and pressure percent. You know, the volume and pressure percent are these. No, they're restrictions. These aren't always true. And so when is it true, when is it false? And so for gases, we have to delve deeper into how we visualize a simple gas mixture like air. So let's talk about this. And this one is just wrong. So erase this. So let's take a 1 liter container of air at 1 atmosphere. Inside this container, going to have some nitrogen. Mostly nitrogen. It's 80% nitrogen, so that means 80% of the molecules here are nitrogen, and only 20% of the molecules here are oxygen. So 80 to 20 ratio. And so it's always true in this mixture that it consists of 20% by mole O2, 80% by mole N2. It's always true. But the others depend on how you visualize what the gas is. So let's take a look at this here. For example, if I separate the oxygen from the nitrogen, what am I going to have? Let's separate the oxygen from the nitrogen. What will I have? So how much nitrogen am I going to end up with? 80%, which is how many liters?
0.8.
Okay, I'm going to end up with 0.8 liters. Nitrogen. Plus, how many liters of oxygen? 0.2 liters of oxygen. So if I take 0.8 liters of nitrogen plus 0.2 liters of oxygen, how many liters of air will I have? I'll end up with 1 liter of air. What's the pressure of the nitrogen here? Is it going to be 0.8 atmospheres? Oxygen plus 0.2 atmospheres of nitrogen and oxygen. I'm going to get 1 atmosphere of air. Yes?
No.
No? Why not?
Yes.
No is the correct answer. This is wrong. But wait a minute. Isn't it Dalton's law? That means Dalton. Do you guys remember Dalton's law of partial pressures? Partial pressure of A plus the partial pressure of B yields P total. Dalton's law of partial pressures. The sum of the partial pressures is equal to the total pressure of the gas mixture. Do you guys remember that?
Yeah.
So that means Dalton's law is false? And then if it's true, then it's got to be 0.8 atmospheres plus 0.2 atmospheres equals 1 atmosphere, correct? No, maybe, let's rethink this. If I take this box here, this box is actually going to be, how many atmospheres of nitrogen, do you know? This box is actually 1 atmosphere of nitrogen. Let's shrink it down. And so in other words, when I think about pressure, pressure is the force of the collisions against the walls. So what I do is I separate out the nitrogen and I keep the density the same, like you were saying, so that I have the same number of collisions with the wall. And so the pressure of this is going to be 1 atmosphere. And for oxygen, I have so much fewer, as far as the molecules go. Anyway, I have a lot fewer molecules of oxygen, so I need a smaller box to generate the same pressure. And so this has got to be 1 atmosphere. And so it's going to be 1 atmosphere plus 1 atmosphere is equal to 2 atmospheres total of air. Is that right? Is that right or wrong? No, this can't be right either. You know what this has got to be? This has got to be 1 atmosphere plus 1 atmosphere is going to give me how many atmospheres of air? 1 atmosphere. It's because of the way I add it. I just attach the 2 boxes and lift it. You know, there's no pressure difference, so it'll mix quite nicely. And so it's 1 atmosphere plus 1 atmosphere gives us 1 atmosphere of air. 1 atmosphere of nitrogen plus 1 atmosphere of oxygen gives us 1 atmosphere of air. Is that a violation of Dalton's law? No, this is not a violation of Dalton's law because do you know Dalton's law is restricted? Right? It's not valid all the time. Dalton's law, this is a failure of Dalton's law because it's not valid. This is an example of what we call Avogadro's law. Have you heard of Avogadro's law? Avogadro's law is that the volume is proportional to the number of moles. So if we double the number of moles, we'll double the volume. Triple the number of moles, triple the volume. That's Avogadro's law. In other words, volumes are directly proportional. That means Avogadro's law says this, that the sum of the partial volumes is equal to the total volume. So if I take the volume of N2 plus the volume of O2, I'm going to get V total. That's Avogadro's law. And so what happened to Dalton's law? Well, Dalton's law doesn't apply in this case. When does Dalton's law apply? It applies to this mixture as well. It just doesn't apply to this way of visualizing the mixture. And so let's see the Dalton's law visualization. This is Avogadro's law visualization. Next, we're going to look at the Dalton's law. We'll take the exact same mixture and now try to visualize it using Dalton's. We don't call it Dalton's law visualization or Avogadro's. We have simpler words for it. But if you were to visualize this in terms of Dalton's law, how much O2 do we have? How much O2 do we have? Whatever you want. Tell me how much O2 I have. 1 liter. I have 1 liter of O2. 1 liter of O2. And how much N2 do I have?
1 liter.
I have 1 liter of N2. And so if I have 1 liter plus 1 liter, this should give me 2 liters of mix. True? True? 1 liter plus 1 liter should equal 2 liters, but it doesn't equal 2 liters. What does it equal? It gives us 1 liter. And so, you know what? Avogadro's law just failed here. And what's the difference? Well, if I have the N2 in a one, actually, I just have this backwards. Sorry. Let me do the N2 first, and then the O2, just to keep it consistent. If I put all the molecules of N2, I'm going to remove all the red molecules and just leave the blue molecules. If I do that, what's the pressure going to be? Is the pressure going to be the same? No, because I don't have any red molecules colliding with the wall, so what is the pressure? It drops to 0.8 atmospheres here. And so I have 1 liter of N2 at 0.8 atmospheres. How much O2 do I have? I have 1 liter of O2 at, now I have very few collisions, 1 liter of O2 at 0.2 atmospheres. And so now when I do 0.8 atmospheres of nitrogen plus 0.2 atmospheres of oxygen, I'm going to get 1 atmosphere of air. So rather than calling this Dalton's law or Avogadro's law, we have different terms for this. We call this one a constant volume. We call the previous one constant pressure. So Avogadro's law is constant pressure. Dalton's law is constant volume. Way of doing this. It's the exact same mixture for both of them. And so we could summarize this by saying this. What 20% O2 means is this. This is mole percent. It means I have 20 moles of O2 per 100 moles total, which is the air. Okay, this is called just the percent, this is called a mole fraction. So mole percent, mole fraction. Nothing new with that. But it turns out the mole fraction, which is always valid, can give us a volume fraction as well. The volume fraction would be 20 liters of O2 for every 100 liters total or of air. And so the volume fraction, however, the volume fraction is not always valid. When is the volume fraction valid? Okay, when is that? Constant pressure or constant volume? Constant pressure. So we call it, under conditions of constant pressure, the volume fraction is equal to the mole fraction. And then we have a pressure fraction too, 20 atmospheres of O2 for every 100 atmospheres of air, or total. And the pressure fraction is valid under conditions of constant volume. Okay, so if we're dealing under constant volume, then this is true. If we're dealing under constant pressure, then this is true, and this is true no matter what the conditions are. So if we know this, then we know how to deal with these mixtures, because sometimes the mixtures are given to you in terms of atmosphere. You know, they pump in 5 atmospheres of hydrogen gas into the mix. What is the percent? Sometimes the mixture is given to you in liters. Sometimes it's given to you in grams, where we'd have to convert to moles. Sometimes it's given to you in moles. And so the mixtures are given to you in different ways, and it's easy to get tripped up. You know, it's easy to get tripped up if you don't know. You know, oh, is that 0.8 liters of nitrogen at 0.8 atmospheres? Is that right? 0.8 liters of nitrogen at 0.8 atmospheres? No, that's not right. You know, it's 0.8 liters of nitrogen at 1 atmosphere, or 1 liter of nitrogen at 0.8 atmospheres. Okay, and so, but it is, you know, when you're given a mixture, sometimes it's hard to figure it out. Unless you really think through these. All right, the next section, this is stoichiometry, so there are some mixture problems in there. You take a look at those. And then we're going to kinetic molecular theory. section after stoichiometry. Kinetic theory. In other words, when we think about a gas, kinetic is just motion, so the motion of molecules, the motion of the particles. A gas is mostly empty space. Let's just take a pure gas this time, rather than a mixture. And these particles, gas particles, undergo straight line motion until they collide with something. They can collide with other molecules as well. And so it's undergoing random straight line motion, and their collisions that generate the pressure of the force per unit area. But if we have a gas at 25 degrees C, are all the particles moving at the same speed? No. In fact, at 25 degrees C, we have a distribution of speeds. We call it the speed distribution. And what does the speed distribution look like? Yeah, it's kind of a bell-shaped curve with a tail in the end here, high energy tail. And so let's point out some features of this. On the y-axis, we plot population. That is just the number of molecules with this particular speed, which is plotted on the x-axis. The speed is also called the velocity. The velocity is given the symbol v or u. In our book, we use u. So at the peak here, this velocity here is called the most probable. This is going to be the one with the highest population. But is the most probable velocity also the average velocity? No, the average velocity is going to be skewed a little bit to the right because of this asymmetry in the curve. And so the average velocity is around here. We call the average velocity the mean velocity. But we are going to look at something that's kind of interesting. We're going to look at something called the RMS velocity. RMS stands for root mean squared. So what we'll do is this is equal to the average velocity, which I'll call u bar, squared, and then we'll take the square root of that. And so you take the average squared and take the square root, and what do you get? You get the RMS. Well, what's the difference between the RMS and just the regular old average? It turns out there's a slight difference. The slight difference I'm not going to get into. I just want to say this. What is the RMS speed? The RMS speed is, if you could take all the molecules in here and give it one speed, what would the collective speed be, or what would the effective speed be, or what would the average speed be? And so this is the effective speed of the collection of molecules. And so we know that some molecules move slow, some move fast, but if there's a way to distribute this so that all the molecules move at exactly the same speed, then what would that speed be? That speed would be the RMS speed. And we'll call it the effective speed of the collection of molecules. Well, the temperature is related to the speed. How is the temperature related? The temperature of the gas related to the speed? Well, one thing that happens is temperature and speed. Let's take a look at this. And so, let's say at 25 degrees C, I have a population distribution that looks like this. This is 25 degrees C, and then I have a URMS that's here. What would happen if I increase the temperature? If I increase the temperature, then the fraction of lower energy molecules decreases, and the fraction of higher energy molecules increases. And so in other words, we shift the population to the right. When we shift the population to the right, the URMS shifts as well. Okay, at lower temperatures, this is T greater than 25. Let's see. At lower temperatures, we're going to shift the population to the left. So increase the number of lower energy, decrease the number of higher energy, and then you can see the URMS shifts down. And so it turns out the URMS and temperature are related. You can see the URMS changes with temperature. And so how exactly is temperature and speed related? You would think it's like this. You know, I would think it's like this. I think that the temperature is proportional to URMS. Would you agree? You know, the higher the temperature, the greater the speed. The greater the speed, the higher the temperature, the effective speed. Does that make sense? I would think it's like this, but this is actually wrong. Just slightly wrong. It turns out that the temperature is not directly proportional to the speed, the RMS speed. It turns out that the temperature is directly proportional to something we call the average kinetic energy, E bar K, where E bar K, the average kinetic energy, is equal to 1/2 m U RMS squared. And so in physics, this is one of Newton's laws, the energy is equal to 1/2 mv squared, the kinetic energy. Have you heard this one? If not, you don't have to worry about it. But it turns out that, okay, the temperature is directly proportional to the average kinetic energy, which is directly proportional to the square of the speed. And so yes, it is related to URMS, but it turns out to be a non-linear relationship because we have this squared term here. That's it for that. So, what can we do? Well, let's go ahead and do some simple calculations. You don't have to derive these equations. For example, this equation is going to be given. Well, in physics, what do? You memorize this. EK, kinetic energy, KE, is equal to 1/2 mv squared. The only difference is we use U instead of V. We're using URMS to get the average kinetic energy. And so, what about URMS? How can we get that? URMS, let's say URMS is going to equal the square root of 2E bar K divided by M. Is that right? Just rearrange this equation and solve for URMS, right? And so the square root. It's going to be slightly different than that. URMS is going to equal the energy, the kinetic energy. And the kinetic energy for this gas, do you know there are 3 types of motion? Are you familiar with that? There's something we call translational motion, just going from point A to point B. And then there's rotational motion. And then there's vibrational motion. For ideal gases like this, all we're considering is translational motion. We don't think of these particles as rotating or vibrating during that. And so it turns out that the kinetic energy can also be known as 3RT over the molar mass. Yeah. This equation is going to be given. And so in other words, it's the square root of the energy over the mass. But you don't have to worry about that. All we have to do is some calculations. But we got to make sure we got this equation right. So if the molar mass increases, what happens to the speed? As the molar mass increases, the speed actually decreases. And that seems to make sense, the heavier it is, the slower it's likely to move. The URMS. And so let's do an example calculation. Calculate URMS for air. What is the root mean square speed of an air molecule? But air is a mixture, isn't it? It's a mixture, so how do we handle that? Well, the easiest thing to do for gas mixtures is to, well, if we need the molar mass, the easiest thing to do is just to use the average molar mass of air, in other words, rather than doing a graphical method, which we could do. We could do graphical or whatever else. But, so we have this. Let's go ahead and set it up. So URMS for air, let's do it at 1 atmosphere and RT, room temperature. This is going to equal 3 times R. Which R should we use? The 0.08206 or the 8.3145? Well, if you try to use the 0.08206, the units won't work out. And so we're going to use the 8.3145 joules per mole Kelvin version of R. Do you have both memorized? Times T, 298 Kelvin, divided by the molar mass. The molar mass was, what, 28.8 grams per mole. Take the square root of this. And what will the speed be? So why don't you go ahead and calculate that? Do the units work out? No, the units don't work out, do they? That's why you need to know something. You need to know what a joule is. Well, joule is defined as a kilogram meter squared per second squared. Okay, now do the units work out? Yeah. That's in kilograms, so we have to change this to, from grams to kilograms. So that's easy. Now do the units work out? Yes. And so what do you come out with for the speed, RMS speed? Did you get 508? You have 508 units? Meters per second. 500. That's like 500 meters in 1 second. Is that fast? 500 meters in 1 second would be equivalent to how many miles per hour? 500 meters per second would probably be over 1,000 miles an hour. That's fast, right? That's extremely fast. And so this is it. URMS speed is, if we visualize every single molecule of air in this room moving at the exact same speed, what would that speed be? 508 meters per second. That would be the speed that we would have at 25 degrees C. You know, but there is a distribution of speeds, right? Some moving fast, some moving slow. But we know that air is a mixture, and so we can take, you know, the oxygen and nitrogen and just kind of come up with an average, or we could separate it. Let's go ahead and separate the mixture. Why don't you calculate the URMS for nitrogen at RT in 1 atmosphere? What would the speed of the nitrogen be? Nitrogen has a molar mass of 28.02 grams per mole. Meters per second. Okay. 513 meters per second. Is that what you guys got? You mean you didn't get that? What did you get? 505? 515 meters per second? Sherry, you got 515? Who else? 515? All right, it sounds like more people got 515, so let's just go with that. I haven't checked these answers, but 515 meters per second for nitrogen. Calculate URMS for oxygen. Here. $482. Others get the same amount? Okay, 482. So you can see that the oxygen is moving a lot slower than the nitrogen, and their weighted average speed is 508. That's because we have more nitrogen than we have oxygen, so the average is going to be much closer to nitrogen. We could have done this using the graphical method too, but it's not really. I mean, figure out the 508 using the graphical rather than the average molar mass here. But going back to this, does that mean the nitrogen has higher kinetic energy? You know, it's moving a lot faster, 515 meters per second, and so shouldn't the nitrogen have higher kinetic energy than the oxygen? True or false? False? That's why. I mean, the nitrogen is moving faster, it's got to have more kinetic energy. It's moving faster. Sure? Right. Its mass is way less. Actually, both of these have the same kinetic energy, and all three of these have the same kinetic energy because all three are at the same temperature, and therefore they should all have the same average kinetic energy. And so it has to do with the mass. So if you have a nitrogen molecule coming and hitting you at 1,000 miles per hour, did you feel it? You don't feel it at all, right? But if you had a truck coming at you at 1,000 miles an hour, then you would feel that, because that would have a different kinetic energy. It's just a math. And so let's go ahead and calculate the kinetic energy, the average kinetic energy, to show that all three of these should equal, or be the same. So let's go ahead and calculate the average kinetic energy for nitrogen first. E bar K is equal to 1/2 mu/RMS squared. And so the equation is going to be given. You just have to plug in the numbers, that's all, to do the calculation. And so go ahead and do this calculation and see what we get. And then repeat the calculation. We're going to do for nitrogen, and let's do for oxygen. And hopefully they come out exactly the same as they should. So E bar K
stands for mass.
Mass, right. Anybody close? Somebody have the answer? Well, unfortunately we're out of time, so we'll continue this next time, Wednesday.
8.71
What, how,
to the 6.
what did you get?
8.7.
8.71 times 10 to the 6 units.
3.7.
3.71 times 10 to the 6 units.
Is that too big?
I got 3715.8.
3715.8 units. J?
Yeah.
All right. So if the nitrogen comes at you and hits you with 3,700 joules of energy, will you feel it? Then you got to know, what would 3,700 joules of energy do? 3,700 joules of energy is around 1,000 calories of energy. 1,000 calories of energy would do what? 1,000 calories would heat 1 milliliter of water by 1,000 degrees C, or a liter of water by 1 degree C. What do you think? So how much blood do we have in our system, and we would increase the volume, the temperature of that? Does that sound right? A molecule of nitrogen that packs that much punch. So So let's think about this when we go back to it on Wednesday.